In the previous section, we used pipelining to increase the throughput or speed of an FPGA loop. By the end of this module, you will be able to use pipelining to increase the throughput or speed of a single cycle time loop. So if we take a look at this slide, we've got a single cycle time loop and we've got some code in there. So notice that we've got a piece of logic over there, and what we can do is we can take that logic and break it up into two pieces and then pipeline it. So as you can see in this slide, we are going to try to reduce the total length of the code inside the single cycle time loop by pipelining. So we've taken that logic and we've broken it up into two pieces, and the next step we're going to do is pipeline it. So in this slide, we see that we pipelined it and we've taken those two pieces and we've used shift registers to implement our pipelining. So this is just the same thing that we talked about before in previous slides. And we could also have implemented this pipelining using feedback nodes instead if we wanted to make the code a little bit more readable. Okay, so let's talk about some caveats with pipelining. So one, it might require your code to be restructured. This is more of a concern if you're using shift registers to implement your pipelining, because you're going to have to move things around, and things, instead of going from left to right, they go from top to bottom. This caveat is greatly reduced by using feedback nodes instead. If you use feedback nodes, as we see at the bottom, we still preserve the left to right kind of readability of our code, but we do gain the advantage of having pipelining. So the other one caveat that I want to talk about is the latency for pipelining. So the latency for a pipeline with n steps, the final output is going to be invalid until the nth iteration. Okay, so let's talk about this a little bit. So if we take a look at the code at the bottom here, let's kind of walk through it. So on the very first iteration, we're going to get an input, and that's going to go to process data. Okay, so the very first iteration process data is going to send data to that first feedback node. Now the second iteration, what happens? Well, that data, that valid data, comes out of the first feedback node and goes to the second process data, and then it travels on and puts it into the second feedback node. Okay, and now on the third iteration, finally, we get that valid data out of the second feedback node. It goes into the process data, and the output of process data is our first valid output. And because this is a three-step pipeline, we didn't get valid data until the third iteration. To deal with that, in this particular block diagram, if we take a look at the bottom, we have implemented something where we're looking at the iteration, and we're seeing if it's greater than or equal to 2, which means it's the third iteration of the single cycle time loop already. And then we're going to output a true on the third iteration and later. So in this case, if you look at that case structure, we're only going to output a result from the third iteration and later, because that's the only time when that output will be valid. Okay, so let's do exercise 6.3. And if you're able to at this point, this is a good time to do exercise 6.3 pipelining. For now, I'm just going to give a overview walkthrough through this exercise. Okay, let's take a look at exercise 6.3, pipelining. Okay, so what I'm going to do first is I'm going to open up this VI for pipelining, which is executing on our FPGA. And I'm going to take a look at the block diagram. So if we take a look at this block diagram, right now there's no pipelining going on, right? So in the single cycle time loop, notice that we're trying to make it execute at a clock rate of 80 megahertz. So we've got our input here. It's going to process data. It's going to another process data and another one and the result. So we've got 3 chunks of code right here. Okay, so if I were to hit the run button and try to compile it, this would actually fail. And this code that we have here is not going to be able to fit within one clock cycle of an 80 megahertz clock. Okay, so let me show you a picture, a little screenshot of what the timing violation analysis window would have looked like. So if we take a look at this, notice that over here, we've got our path 1. We got a requirement of 12.49 nanoseconds. And that requirement comes from the fact that we want to use an 80 megahertz clock over here. Okay, so that means everything, all the code inside here needs to finish within 12.49 nanoseconds. If we go over here to total delay, notice that the code that we have here takes a total of 27.47 nanoseconds to execute. Just by looking at that, we can see that, okay, that's much greater than 12.49. So what can we do to try to make our code fit within 12.49 nanoseconds? Well, we can examine the timing violation analysis window, and let's take a look at our code here and see how it breaks it down. So if we take a look at that first process data VI, notice that the total delay here is 8.71. Okay? And if we look at that second process delay, that's going to take 8.79 nanoseconds. And that third process data that we have in our VI is going to take about 8.31 nanoseconds, at least on this compilation. So if we take a look at that, all those process datas are well below 12.49 nanoseconds. So if we were able to pipeline this and we were able to execute those process datas, those three, in parallel instead of sequentially, then we can actually meet this requirement of 12.49 nanoseconds by a lot. Okay? So let me close this. And let's go to our solution. So this is what we have now that caused that timing violation because we're executing all these in sequentially. I'm going to close this, and I'm going to go to pipelining solution. So if I was to open this up and do it this way, notice that this is still 80 megahertz, but now I've done some pipelining in here. So I've added this feedback node here and a feedback node here as well. And now we're going to have a result that is pipelined through this algorithm. Okay, so over here, just like we saw in the previous slide, this is just some code to only output a result after that we're going to wait until the third iteration and later to actually output a valid result.